Perfect. Very cool. Okay. Am I visible? That's the wrong camera. Here we go. Okay. So we've got this item, this ball that's traveling in this circle. And as you said perfectly, it's the fact that this direction is changing. That means that the velocity changes, even though the speed is the same. So as this is moving in this direction, if we take a freeze frame of it right now, mid movement, what is the in which direction is that's fine, no worries. Study mind. Um, if I were to draw an arrow from its center of mass to the direction that it is currently traveling, which way would I draw it in this freeze frame snapshot moment?
Well, um, like you draw it directly downwards or directly upwards, depending on which way it's going.
Okay, so Anna's saying it's traveling directly upwards. Hi, Lisa. Can you hear and uh, see me and everything okay? Okay, no response. I was going to get multiple ideas. Oh, here you are.
Yeah, it takes me a while to like work out how to unmute things.
Okay. Um, so where would you say would you agree with this green arrow as the current velocity in the snapshot?
I
Or would
was
you say that-
thinking more that it feels like around it.
So you would say that it's kind of like that.
Yeah, or maybe
If
the
it was
opposite
drawn.
way.
Yeah. Okay. Um, so you're kind of you've answered different questions, but one of you is right for the question I've answered. So Anna, you're correct that in this current moment, this ball is traveling directly upwards, but the path it takes because of the acceleration, if we let the motion play on, it will kind of follow the curve. Um, but this is, let's call this snapshot velocity. And the way you can kind of prove it, the good thing with physics is, especially with mechanics and these kinds of topics, you can kind of test them out yourself. So if you got a piece of string or something, a piece of rope or something, and you tied it to some kind of weight, it's not a key. Like you put a key on one side and you started spinning it around, and that represents this red object traveling around. And you suddenly let go of the rope, the key would travel in a straight line in the current direction that in like where it was traveling in that moment. Like it would leave the circle and go in carry on going in a straight line. So the kind of objectives velocity is always kind of always leaving the circle. So something's got to be keeping it in. Something by definition then has to be acting this way to kind of keep it in that circle. So what could that be?
Frictional force?
Fictional force?
Yeah,
Was that fictional or frictional?
no, like friction. No.
Friction. Okay. Right.
Gravity,
Gravity. Okay. Any other ideas?
tension, I guess, if it's like like I don't know, like you're spinning something in the air attached to a string or something like that.
Yeah. So what was the word you said? I didn't hear the first word.
Tension, tension.
Tension. Okay. Okay. So some ideas here. Gravity is kind of only physically acting downwards. And if you imagine this traveling around, let's see if I can make this work. If this is like, oh, it didn't rotate. Yeah, if this is kind of rotating around like that, do you see how the blue arrow still stays pointing inwards? So the direction keeps changing.
Yeah, I was thinking like a planet around the sun or something like that.
Sure, that in that case, yeah, gravity would be the specific force that's acting, but like the role it's playing would be a different name in that case. Even generally would be a different thing. So here, the force that's acting is called centripetal force. So this is the first time I heard of it when I was in A level. Like centripetal force was a brand new word for me. I heard of centrifugal force before, but centripetal force was I never heard of that. So I'll get rid of these guys. So friction, it's not really friction. Gravity, I can see where you're thinking that, and tension would be acting. Actually, let's talk about tension really quickly. So if this was a rope and we're swinging the key around, the tension would be acting kind of. Let me use this color. So here's the rope. There'd be tension at your finger, pulling it this way, and on pulling this way, and on the key pulling it this way. So both of those kind of would be tension. So no, it wouldn't be tension. But let's go back to this arrow. But it's acting along the rope. I'll give you points for that. So these are the two forces that we want to think about. Centripetal force, centrifugal force. Now, only one of these is a real thing, and one of these is what we call a fictional force or a fictitious force. So that when you said frictional and I heard fictional, that's kind of where I was thinking. And I thought maybe you're one step ahead, but you're right on track. So centrifugal force is the fictional force. It's not a real thing. It's the feeling of being pushed outwards. So imagine this is a car going around a roundabout. I'm going to just move it around because it's going to be easier to visualize a car going around a roundabout in this direction. So this car is going around this roundabout. And if you're sitting in this car, you feel like you're being pushed outwards, right? If this car's going really fast around and it's turning, you will feel like you're being pushed outwards. And that's because from your perspective, you're traveling in this snapshot velocity direction, which is out of the circle. So that's why it feels like you're being pushed into the door, the outside door. And that's what happens in a centrifuge. A centrifuge is basically something. So NASA first started talking about centrifuges, where they had this big machine, around like a big swing on a pivot, and there's a box here and a weight on this side, and a person would be sitting inside here, and this would spin really fast around the pivot. And the point of that was to figure out how much acceleration one person could take before it got really dangerous. So this was NASA centrifuge. So it's basically a spinning force, and that's where the spinning kind of idea came. And if you're being centrifuged too much, if you're spinning at too much of an acceleration, then basically the problem that happens is the oxygen in your brain gets pushed out of the brain, and you can kind of imagine why that's a bad idea. So that's the kind of limit they were trying to find. But anyway, so that's what a centrifuge is. So it felt like a centrifugal force, but this is not really a force that exists. It's only the centrifugal force is you trying to travel in your direction, but the car's door is stopping you from leaving and it keeps you pushing in, but it feels like you're being pushed out, but you're not being pushed out. So centrifugal force is not a real thing. I'm going to put it across here. But there is a centripetal force. And I talked about the acceleration in this NASA centrifuge. This acceleration is this blue arrow. So let's write it here. This is acceleration. So I'll label it A. And A equals centripetal force over here. Okay, so that's the force that's pulling you inwards. I'm going to think of something. Where was I going with that? Come back to me. So that's acceleration that's keeping you in. So we've got a velocity, we've got an acceleration, and that's the acceleration is what causes the change in velocity, which it only actually causes the change in direction. How would, in this situation, in this perfect ideal world, it's the fact that this acceleration is perfectly perpendicular to the velocity that means it has no effect on speed. Basically, two factors that are acting perpendicular to each other don't have any interaction with each other. When you start maybe you've already resolved forces in mechanics and the other like projectile motion and stuff, and you resolve forces. If you haven't, then you'll do that soon. But if you've got a projectile that's traveling at some angle, it's kind of hard to work with angles. So generally, you'll change that into the vertical component and the horizontal component. And then you only have to consider one aspect at a time. And again, that's the kind of same idea here. When you're working with two things that are completely perpendicular to each other, you don't have to think about both of them because they don't interact with each other. So it doesn't affect, the acceleration doesn't affect the speed, but it only changes the direction because it's perpendicular. Okay, so reading the notes I've got in front of me, an object moving in circular motion has a constant speed and a constantly changing velocity. As velocity has both magnitude and direction, therefore the object must be accelerating. We talked about this. This is known as centripetal acceleration. Right. They then start talking about Newton's first law, which is, I guess, good to include into this part. It's a really brief little segue. Anyone remember Newton's laws, and especially the first one? But if you say a different one, that's points as well.
Is Newton's first law the one where an object will remain at rest if it is at rest, and an object will remain at motion if it is in motion, if no external force is applied on it?
Perfect, absolutely. Rest / in motion. You said it a better way, but I'm going to write it in a shortcut. In motion, unless acted on by a net external force. So a lot of people forget this little part. It's the word net. So it's not just the fact that there's another force outside acting on it, because if you've got two forces that cancel out, it's still an external force, but they cancel out. So you want to include the word net, but otherwise, perfect, very good. Just for completion, what are Newton's second and third laws?
Newton's second law is F is equal to ma.
Perfect.
And then Newton's third law is that the every force has an opposite and equal reaction force of the same type.
Perfect. Very good. Every action has an equal and opposite reaction. Good. So from Newton's first law, this is remaining in motion. but it's perpendicular, so it's not actually affecting the speed. It's kind of the same kind of concept we talked about. But because it's accelerating, there's got to be some force acting on it, and this force is centripetal force, and it always acts towards the center. Okay, good. Another key term in this region is the angular speed. So we know what speed is, but angular speed, or omega, it's kind of a curvy W. Have either of you come across angular speed? And if so, do you know what it is?
Is the speed of the angle at an object that rotates through per second.
The speed at the angle that it's rotating. Kind of.
So, like the object is like rotating at like an angle, but it's how it goes through per second is how I was thinking. I don't know if it's not.
Yeah, basically. Like if you I'll draw a smaller circle here. Oh, it's filled in red. So where's my last one? Okay. If this object here is traveling around and it takes 3 seconds to end up here, then it's the speed. Basically, the distance is now, instead of a straight line in the speed, it goes distance over time. It's a curve, basically. Right. If you want to, the key thing with angular speed is there's only a couple of equations to kind of worry about. So the first one is the angular speed equals the velocity that this object is traveling at over the radius. So angular speed, if you increase the actual speed that the snapshot velocity. So if you increase that velocity, then the angular velocity increases, or if you decrease the radius, then the angular velocity increases. Like if you're spinning that key around your finger again, and then you keep spinning it with the same force, but you start wrapping the rope up on your finger so it gets shorter, you'll realize that the key travels faster, but you're spinning it with the same force. So that's because the radius is decreasing. So angular speed is a form of velocity, really, but you kind of accounted for the fact that its direction is changing in the word angular. So angular speed is v over r. Now, the actual definition for it is it's the angle an object moves through per unit time. So that's the actual definition for it. And then the good thing with physics definitions is you can kind of make the equations from that as well. So to deal with the angle in this case, we'll talk about the angle in radians. So one whole revolution is 2 pi radians. Have you guys come across radians before?
Yes.
Yeah. And have you, Lisa?
Yes.
Yeah. Okay, good. So how many radians is one complete turn?
180.
That's not radians.
2 pi?
2 pi, exactly. So if this object starts in this left position and goes all the way around, one complete turn, then it's traveled 2 pi radians. And if you measure how long it takes to do one complete revolution, that's just time.
Sorry,
So
I
that's
just
another
have
formula.
a small question.
Sorry?
Sorry, I just have a question
Yeah, of course.
because I haven't done angular speed yet. So the v is velocity,
Mhm.
but why are we taking that as distance? Or why are we taking that as like the angle that we have turned? Like, why are we taking v as 2 pi?
So, oh, these aren't derivatives. This is just kind of omega also. You can write this as omega also equals this. They're separate equations.
Oh, I see. Okay.
Yeah. But then I've just written it like this because
Okay.
they
Yeah,
equal omega.
So they're two separate equations that
Yeah.
both equal to omega. Okay, fine. Understood.
Cool. But you can derive this a little bit further. So say instead of telling you that it takes 3 seconds to go around once, they tell you that the frequency is 0.33333 or is 1/3. So instead of converting that to time, you can kind of keep that in one equation and you can just use 2 pi f because you know that frequency is 1/time. So you can kind of substitute that in. Does that make sense?
Yes.
Cool, perfect. Okay, so we talked about radians already. And then if you want to work out the value of the acceleration, the centripetal acceleration, that's another thing that they can ask you. These questions, they seem scary because angular acceleration, angular speed, centripetal acceleration, lots happening. But usually they just give you the values and you plug them into the equation and you get the answer. Like you might have to move some stuff around, make something else a subject. Pretty straightforward most of the time in what they ask you to do. So it's not too scary of a topic. Anyway, to calculate centripetal acceleration, you've got acceleration is, so what's the units of acceleration generally?
Meters per second squared.
Yeah, perfect. I'll write it like this. Because we can also make up equations. If the units match and we're talking about the right properties, then you can kind of sometimes also make up equations to make it easier for yourself. So meters per second squared what else could we include in this equation? Meters per second squared. Acceleration could be equal to something that we've got on the left side.
Frequency squared multiplied into the into distance, but it's nothing in unit meters.
Okay, I can see the frequency squared is like the s squared at the bottom. I can see that. What if there was something else that was meters per second already?
Oh, velocity.
Yeah, velocity.
Velocity into frequency, or velocity by time.
Velocity. Okay, velocity by frequency.
Velocity multiplied into frequency.
Yeah, I mean that makes sense unit-wise, but it wouldn't conceptually like it's kind of awkward to kind of combine the two. So you can make velocity squared over the radius. So it's kind of similar to this. So you've got meters per second times meters per second, and this is a unit of length, which you've already used before. So you know that you can kind of use these guys together. And so this cancels out. And you get meters per second squared. So this is a pretty straightforward equation. Actually, I'll leave that one as well, because if you remember this one, then this one kind of is just an extra v on top. Cool. And that's centripetal acceleration. We talked about centripetal force. So can you think of an equation that combines force and acceleration?
F equals ma.
Yeah, perfect. So centripetal force then. So the force equals mass is still going to be mass of whatever you're talking about. And then instead of acceleration, we can use this concept here, the centripetal acceleration times v squared over r. So we can just say mv squared over r. So again, not too complicated of a formula to have. Okay. Does that all make sense with these?
Yeah.
The concept of angular speed and how centripetal forces and stuff work. Because I'm thinking I'm going to pull up some questions next. Some multiple choice ones just to get us warmed up. Let me look. Yeah, we can do this one. Okay, let me stop sharing screen here. Share. Oh, no, didn't want share. Yeah, okay. Okay, so a lead ball of mass 0.25 kilograms is swung around on the edge of a string so that the ball moves in a horizontal circle of radius 1.5 meters, and the ball is traveling at a constant speed of 8.6 meters per second. Calculate the angle in degrees through which the string turns in 0.4 seconds. We've talked about some of the equations already.
I'm not sure.
Okay.
But would the answer be like oh, yeah, but would the answer be something like 8.6 into 0.4? Or is that completely wrong?
6 into 0.4, 8.6 into 0.4. That's somewhere involved.
Okay,
That's
because yeah, because what I was wondering if we could do angular speed is equal to 360 divided by t. But like instead of 360, we put like an x because we don't know the angle and we have to find the angle. And then we rearrange to find the x, but I wasn't sure if that was correct.
Okay. Yeah. So you're on the right lines. We do have some values. So with questions like this, where I'm not sure which formula or kind of where to begin, what I would do to start off would be I just write down every value that I have. I'll just make a list of it. This really worked for Subat because you got the 5 equations and you don't know which Subat equations to use. But I kind of expanded and did that in other things as well. So that will put into perspective, that should give you ideas into like where to go next as well. So I'll start it off, and the starting step is kind of what you were just saying. But okay, so we've got mass. This is really thin. How do I make this thicker? Okay. Yeah, okay, that is that. Is 0.25. We've got on the end of a string, horizontal radius. We've got radius, 1.5 meters. And we've got the speed, the constant speed. So this is what I like to think of as the snapshot speed. So it's the speed in the straight line before the acceleration. That's speed. It's 8.6. So what was the first equation you said that we could use?
Omega equals to 2 pi by t.
Okay, we don't have a factor of time, so I
Um,
wouldn't use that one.
okay. Because you asked the first equation, that was the one I said.
Hmm. I mean, we do kind of, okay, they have said here the 40 seconds thing, but we'll factor that in. With these questions, I want to work out the kind of value for like the time period that it takes to travel in like a whole rotation, and then kind of break it down into the part of the circle that it travels in 0.4 seconds. But sure, okay, we do have a factor.
Sorry, I'm sorry. Do we use the one for force then?
Mm,
No, because we have mass.
So that will come across with attention here. So that's part two. Okay, so the first step is going to be with omega equals velocity over radius. So work out the angular speed. This is the kind of snapshot speed, remember, this is the kind of in a straight line. So what is the angular speed? And with angular speed, you can do a lot more. So why is it so much thinner again? So velocity 8.6 over 1.5 gives us our angular speed in radians, which is 5.3, 5.73. Okay, rads per second. But that's basically the speed that we care about. That's taking into account the fact that it's turning. So now with this speed, we can kind of just do speed equals distance over time. But so this is our speed value. Distance is the angle that we want to work out. And we're going to stick to radians and convert later. But so let's say speed equals distance over time. but instead of speed, we're using angular speed. Instead of distance, we're using the kind of angle that it's traveled. And time is still time. So we rearrange this to make omega the subject, the angle the subject. So this becomes, what does this become?
Theta is equal to omega times time.
Exactly. Which is 5.73 times 0.4, which I can see here equals 2.3, 2.29. Okay, so that's the distance that it travels, which is basically the angle that it travels in radians. How do you convert that to degrees? How do you convert radians to just normal degrees? So to convert radians to degrees, you will divide by 2 pi. So you divide by the factor that you're in and times by the one that you want to be in. So if you're in degrees and you want to turn into radians, you'll do this the other way around. So 2.29, convert it out of what factor you're in. So you're in radians, so you convert it, divide by 2 pi, and multiply by what you want to be in, which is normal degrees, so 360. Does that make sense? That's kind of how I imagine it. I don't think that's the real proper maths way of doing it, like the maths way of thinking about it, but they always work for me. So you do that, and it gives you an answer of 131. So 131 degrees. One top tip for exams is if I write 131 here, it's not wrong, but it's not the best answer. Why would this not be the best answer? Any idea? Like, how could I make this better?
Is it because all the numbers in the question are given to 2 significant figures, but our answer is given to 3 significant figures? So we should also give ours to 2 significant figures.
Very good. Yeah, we will introduce a level of accuracy that we don't have. So we need to not do that. Very good. Perfect. So 130 degrees. Cool. So the marks, just generally, just so you, for completion, the marks are firstly for the first line of reasoning, second mark, second line of reasoning, and the third mark is the final answer. So not too bad. Okay, so that's basically how we're using the equation. We did kind of do tension. You talked about it already. I was going to skip this question, but you mentioned the mass thing. Do you want to have a go at this question? We've done the equation to do it. I've just not said the word tension in this context, really.
So would we use the force formula? But because force is the force of tension, like that?
Absolutely. So what's the force formula?
So, I mean, I haven't seen it before today, but I think it was something vaguely like m multiplied into v squared by r, I think.
Good, yeah. I'm trying to change color. There we are. Okay. So very good. Force equals mv squared over r. You can do that. There is also, because um, omega equals V over R, there's another one. This derives into mass omega squared R. You can use either one, whichever one you would like to use, because they both get you to the same answer. It's the same kind of properties.
So just checking one thing, sorry.
Mhm.
So when we're talking about V, what's like, where is that speed? Because if we're talking about angular speed, that's the speed of the object traveling around an angle. So where does the normal velocity come from? Oh, okay.
Yeah.
Yeah.
That's why we use the radius in different ways.
Oh, yeah.
Cool. Right. Okay. Take your time with this one.
I'm not sure, but would it be 12.33?
Very good. Yeah, it would be. How did you get that?
So I just used the formula. I stuck to the original formula of mass is velocity squared by radius.
Mhm.
And then I just substituted in mass, velocity, and the radius, and then I got the answer.
Yeah, exactly. And I would do the exact same. So out of the two options, I would also stick to this one because those are the numbers. Well, not the radius, not the time. But yeah, these are the numbers they've given us. So just in case I made a mistake with calculating omega in the last one, I don't want that to carry on to the next one. So yeah, very good. So yeah, 12.3. Um, okay. What do you think of this one?
Sorry, could you scroll back up just to look at the
Yeah, of
radius?
course.
That 0.5.
1.5.
Oh, Again, I'm not really sure, but would it be 12.64 or like 13 or
12.6, what, sorry?
12.6 565.
For the frequency,
No, sorry, for the number of revolutions that the ball makes in one.
revolutions. Um, no, it wouldn't be. But
Is
12.6 is there somewhere. So how do you get 12.6?
So I calculated the velocity using the force formula, so I rearranged it.
Okay.
And then from that, I calculated the speed at the velocity at an angle, the angular velocity, and that gave me 4 root 10. And then from there, I used the angular velocity is equal to 2 pi by t formula. And then I got x, or because I took the angle to be I have to convert it from radians into degrees. Yeah.
Um, so that was 4 steps to get there.
Yeah.
3
It
steps.
was probably not the most efficient way.
So generally a clue, I mean, that was still mathematically correct, but I think what you did, you could have, I think you cancelled some parts out a few times. So this is 2 marks, so probably is only 2 steps, give or take, maybe 1 step, maybe 3 steps. So
Yeah. Yeah, I got 724.7 degrees, which is equivalent to roughly like 2 revolutions.
good, very good. So yeah, 2 is the answer. And there, remember I was talking about the sanity check last time? Like we said in about half a second that this travels 130 degrees. So it's not going to be a crazy number. Like it's going to be around four, maybe 5 times what we've got here. Because if it's traveling around the circle twice. Yeah. Okay. So faster way of doing it, basically. Let me make this bigger. So you started off fine. You used the velocity formula. So you rearranged for velocity equals, what was your rearrangement?
Velocity is equal to root of force multiplied into radians, whole divided by mass.
Perfect. Exactly. So then you got 60 times radius of 1.85 over the mass, which was 0.25, or rooted, which gave you 12.86. So this was where you got already. So I think what you did after, I think you cancelled out because after those 3 steps you were at 12.6. But here you can just go straight to, oh, sorry.
I didn't get 12.6.
Oh, yeah, sorry, I'm looking at the wrong different parts. The other formula gets you to 12.6. But here you got to 19.
Yes, I did.
Velocity, so meters per second. And here, did I say this in my notes? Let me just double check. You convert. I see. Okay. So you've got the omega equals 2 pi f formula already. So let me put the annotate back. So you have omega equals 2 pi f. But if we've got v, then you can just sub in v, like make it in the v term first before you start putting numbers in. and then there's less steps you've got to do. So omega is V over R. So V over R equals 2 pi F. And then make F the subject. F equals V over R. So V 2 pi V. Over R. Did I do that right? No. You're dividing that. Which then you just sub in the numbers, 19 over 2 pi 1.5, so 3 pi. So you can kind of tell already that's 19 over 3 times 3, 9-ish, which is kind of 2. You can do that properly, but you can estimate as well, and you get the right number. So yeah, perfect. Do practice this skill a little bit more of just like combining equations so that you only have to plug in numbers once. We'll do it from the start. But don't do it too much. Like I was just thinking, what if you did it all the way from the start? So you subbed in that V into, it doesn't work, into here and made it all big one equation. That would work if you practice it enough, but it's also really easy to make mistakes there. Because if you've made one small mistake, then it's hard to catch it. But yeah, combining equations is a good skill though. It will save you time if you practice combining the right ones. Anyway, so we've done some questions on it. Circular motion. It's not too horrible of a topic. It's just brand new terms, but the concept itself is not too bad, I would say. What about you guys? Do you agree? Does that kind of make sense? Or will you be looking over that again?
I think I understood, but because I haven't done this before, I will have to go over it.
Sure, yeah. At least you've got the foundation for it now. What are some resources I would recommend? If you go into Crash Course on YouTube, Crash Course is a channel I really like. They've got good animations and good like descriptions and stuff. They are made for AP Physics, which is like the American A-levels. But the content's quite similar, and you just look at the videos that overlap with your syllabus, and they explain it really well. So look at the circular motion one.
Thank
The
you.
animations are better than mine. But yeah, cool. If there's no other questions, then I'll see you guys next week.
Thank you.
No problem. Bye-bye.
Thank you.